Bismillahirrahmanirrahim. Greetings. In this lecture, we are going to prove analytically about irrationality of square root of 2. Now, the title of this lecture will be, there is no rational number x such that x squared is equal to 2. And that is equivalent to say that there is a number x such that x squared equals to 2, but that number is not rational. They're kind of paraphrase of one another. Now, in the previous lecture, we discussed about bounded set, and we discussed about the axiom that is called completeness axiom, which indicates that every set that is bounded above has a least upper bound in the set of reals. And same is true with the set that is bounded below. Every set that is bounded below has the greatest lower bound in the set of real. So we call that one a completeness axiom. And we will be dealing with the least upper bound axiom. And the other thing we did discuss in the previous lecture as a preliminary was about the Archimedean properties. And we are going to use in this lecture. Okay then, let's get started. I'm going to stay out of web, and I have put all of them in writing. Unfortunately, I don't have access to a board, a whiteboard or blackboard, so that I could lecture, talk. But I have put them in writing, which is similar, if not even better. Okay then, let me go and zoom it and start the lecture of today. May I please? Okay, I already mentioned about the title of this, so let me go and see what we have in there. So let S to be the set of all positive rational numbers. Q stands for rational, and we are familiar with this notation, which means belong to the rational, all the rational. So all the positive rationals that a square of them is less than 2. So this is our set. So don't forget that one. We are going to use this set quite a lot in this proof. Now, number one question that we ask is that how do you know such a set exists to begin with? How do you know this set exists? In other words, how do you know this set is not empty? So 1 is a rational number, is that right? Positive rational number. And 1 squared is less than 2, is that right? Therefore, this set is not empty. 1 is there. And second one is that this set is bounded above. And how do I know? Because one of the bounded above elements is 2. Because 2 squared is 4, and 4 is bigger than 2. Is that right? So 4 is not in that set. 4 is in the complement on this set to the right, in a sense. And as a matter of fact, all the numbers bigger than 2 to infinity, every single of them that become considered as an upper bound for this set. So we know so much about this set, and please take a good picture in your head, because we are going to use this set quite a lot. All right? So all of them that I have written here. So let me now change it to the next, if I may. Now here, the axiom that I have already mentioned, is that right? You are familiar with the axiom, I just mentioned it. No, either L, the least upper bound, is in our set S, or it is not. You follow? That either it is or it is not will cause 3 possibilities. L squared is less than 2, L squared equal to 2, and L squared greater than 2. Now, if we can show these two we can show that L is not here and is not here with these two, then automatically it will be that there is such a number that if you square it, you get 2, and that ends up to be the least upper bound of that. So we are going to, as a matter of fact, we are going to show these two, and through the proof of these two, we don't have to go through the proof this one. That spontaneously follows. You follow me so far? Okay, now we make a statement. What is the statement? Is that L square is less than 2, which means we are taking the first case. That means L, which is the least upper bound, belongs to our set, S. Is that right? And therefore, L is a rational number. Now, this statement is false. We know that. But that's exactly what the proof by contradiction is. We take a false statement, and then the conclusion will reject it, always. That's the beauty of logic and mathematics. You can make a false statement, there is nothing wrong. For instance, as I mentioned in the previous lecture, you can say that moon made out of green cheese. Nothing wrong with that. So we go and land on moon, and we find out that moon is solid, and we can walk on it, and it's not made out of green cheese. So what our hypothesis or our statement or our claim was end up to be what, or assumption end up to be false. That's exactly what we are doing, and that is exactly what the proof by contradiction is. So we get the negative of the statement, and we proceed with respect to that, with that assumption, and then at the end, the conclusion we reject it. So we know our assumption was false, for what the negation of that must be true. It's very, very elementary logic. Okay, so based on this, let's go to the next one. May I? Okay, now in this case, our assumption is that L square is less than 2. That means L, or least upper bound, is belong to the set S. Now let's see what happens. Now, L being the least upper bound, that implies that L plus 1 over n should not be in S. This is because this is an upper bound. L is the least upper bound, 1 over n is upper bound. Now, question is, what is n? Now, in this case, I selected n to be a natural number. I wrote it here. N is belong to the natural number. Then the question that you may ask, good question. That's what mathematics is. That's the best way to learn. Keep asking question. Why did you select n, which is a natural number? Why didn't you select x? It stands for any real number. Well, good question, and there are two answers we can give to that. Number one is that we are working with rational numbers, and we assume L to be rational number. So if this one is a real number, which is not 0, then that makes all of them to be a non-rational number. And then we will not talking about our set S, which will consist of rational numbers. That's one answer. The second answer is that we need n to apply it for the Archimedean properties, which we can even call them theorem because some of them could be proven. So Archimedean property goes with the positive integers that I've already mentioned in the preliminary previous lecture, and I'm going to repeat that one more time when we reach that. Okay, so we know n is what? Is a natural number. Now we answered those questions. Now we go and see what happens to 1 plus 1 over n squared, because we are taking L squared to be less than 2. So the rest of them is simple algebra. We expand this one by binomial expansion, which L squared plus 2L over n plus 1 over n squared. Look what I did. n squared, don't forget n is a natural number. The smallest can have is 1. All right? If n squared is smaller than 1 over n. Excuse me, 1 over n squared is smaller than 1 over n if n is bigger than 1. Is that right? Because the denominator of this one is bigger than denominator of this one, therefore this is larger than this for all n greater than 1. You follow me? So what I did, I cut this one off and replace it with 1 over n. And then it become inequality become less than or equal. Do you follow me? If n is 1 is equal, if n is anything bigger than 1 is less than, because I replaced it with a number larger after I cut this one off. That's what I said, less than or equal. The equality holds only when n is 1. Okay, now I go and add this together, very elementary algebra, and I came back to this algebraic expression, which is L plus 1 over n squared is less than or equal L squared plus this, which is end up to this. Now look what happened. My concern is about this. If I can cut this one out and replace it with negative L squared plus 2 or 2 minus L squared, then minus L squared and minus L squared, they cancel each other, so I end up with preserving the inequality, and I end up with exactly what I wanted to show, which is a contradiction. You see, from this I immediately noticed that I need such a thing. I have to cut this one out and replace it with something that preserved my inequality. Okay, that's critical thinking, huh? So let's see how we do that one together. So I have written that one again so that our eye can concentrate, can focus on this, and we go to that. So this is our set. We are going to cut this one off. Now, we go now to what? I have written that one. We go now to Archimedean, all right? L squared less than 2 implies that 2 minus L squared is positive. Is that right? L is least upper bound, don't forget. Less than 2 implies that 2 minus L squared is positive, and 2L plus 1 is also positive. You see that, huh? Okay, now with respect to our Archimedean property, we call this one x, and we let this one to be y. And what does Archimedean property was saying? That n times x will exceed y. So there is an n, in other words, a natural number that if you multiply by one positive number will exceed another positive number, no matter how close or far from each other are they. All right, this is the property of Archimedean that we have gone through that in deep. So here it is. I let my x to be this, 2 minus L squared, which is a positive number. I let my y to be this, so I come here n, which is what a natural number. There is a natural number. The property guarantees that if I multiply by this, will exceed this one. Do you follow me? Think about it. Pause. It's very, very easy really to think that. Okay, now I divide both sides by n, and that ends up exactly what I was after. Look at that. If I divide both sides by n, I get 2 minus L squared is greater than 2L plus 1 over n, which is this. Which means I can now replace that one by something which is bigger than that, so that my inequality will be preserved. Do you follow me so far? Because the aim is to preserve the inequality. So let's go now to the next one. Now the next one is what I just mentioned. So this I wrote, this is the moment of truth, and that is what happened. Look at that. I replace this one by what? By 2 minus L squared. Then I'm preserving my inequality. As a matter of fact, the equality even goes away. So this is what bigger than this. And that means L squared and L squared, they cancel each other. So I'm left with L plus 1 over N, which is an upper bound, because L is the least upper bound, is what? Is less than 2. And that is a great absurd and contradiction. Because an upper bound cannot be less than 2. It's upper bound, is an element from the upper bound, which is larger than L. Only numbers less than L belong to our set. But here it says no, there is a number bigger than L which is belong to the set because it's less than 2. And we know that immediately is what? Is contradiction. Do you follow me? So the contradiction followed. Okay, it's very simple if you think about it, concentrate and contemplate about that. And it's just very simple game of the logic and statements that we are playing with. Okay, then let me zoom this one up and say a few more words, and then we close for today's lecture. May I please? Okay, then what we do for the next lecture, which is going to be very similar as far as the logic is concerned, to show that L squared greater than 2 also leads to contradiction, and then the only possibility left is L squared equals to 2, which means there is a number that if we square it, we get 2, and that is the least upper bound of that set. It's very beautiful, isn't it? Okay, then. I thank you for watching, and I keep repeating. Please, if you notice any error in a sense, or if you have any suggestion for that can enhance my teaching, please indicate that in the comment section below, and you will be doing me a great favor. So please do so. All right, then. I thank you very much for watching. I hope my lectures are productive, and I'm doing that for the favor of the general public students. Again, as always, thank you. I wish you all prosperity and good health, and please stay safe and happy. So long.